All right, so in any case, where I'm at right now is in Canvas, canvas.asu.edu, or you can use the MyASU homepage and click on the course title. It'll take you right here. Well, not directly to this page, but main page of Canvas looks like this, minus the pink. That's just my student view of this. But you'll see on here there's a link to the syllabus, a link to the course textbook, which we'll take a look at in just a little bit. YouTube lectures. So like I have a playlist with all of the lectures. This will be continued when I'm not here. Julia will put things in the same playlist. If you want to see the screen capture with the audio of what went on in class during the day, click there. The most recent one will be at the top of the list, updated sometime after lecture is over. It takes a little while to process video, but other than that, after class. There's also a link to your iMathAS, the online homework site that we use. This is free, and again, if you haven't used the site before but have been in the class before, your login is your ASU Right ID with not your normal password, because I don't get access to that. If you haven't reset it yourself already, the password is listed in what the announcement up above. It's like Newton123 and then the symbols over 123, because it had to have a bunch of symbols in it. So, in any case, spring office hours. As I said, these are going to be updated again when we have some additional information from the math tutoring centers, but there's all sorts of hours available Monday through Friday. Most of these right now are between 9 and 3. But you can see any of the people that work with this course. So these are all lecturers and TAs for the course in either this section or the afternoon section. We're all working on the same thing at the same time, have the same tests and quizzes and all that sort of stuff. So if you have a question about any of those sorts of things, please go see anyone whose schedule matches yours or email. And the email addresses for people related to this class are all in the syllabus. There will be, as I said, additional hours added in later with some specific tutors that have been hired to work with this class in the Math Tutoring Center. And some of them also in the Hassayampa Academic Village, probably like last term we had some there. It just depends on who exactly is available, when and where. But this will be updated to include some additional hours, probably more afternoon and evening hours. So lots of office hours available to go see, ask questions, get things figured out before it's too close to a test or something. Yes?
Is the class in the afternoon the same one as this?
Mm-hmm.
So if I don't get it,
It might be full. Yeah, it's the same course, a different instructor, but yeah, it's the same course, same textbook, same materials. From day to day might say things in a slightly different order, but yeah, same topics. I wouldn't suggest in general just showing up, because that might throw people off. But yeah, if you want to go see again, certainly you can talk to them at office hours. I'm sure it's not a problem, but that class is a little bit fuller than this one. So just so that you're aware. All right, so what I did want to point out here, underneath this, and this will be added to week by week by week, but for this first week, week 1, so this is the week of Monday the 7th through Friday the 11th, but I'll see you on Tuesday and Thursday. This is updated after class to include new assignments, so here's just the stuff that we talked about last time. iMathAS homework number 1 was a how do you use iMathAS sort of assignment. I want to talk a little bit more about iMathAS and answer entry today. Let's see, install GC before lecture. I hope that you were able to do that. The instructions are in the announcement. Reading the textbook, we'll talk a little bit about section 1.5 today and continue with that past today. And complete Canvas quiz number 1. Now, this doesn't open until after class today, but right near the end of class today. But it's open from near the end of class today through tonight, in case you can't get connected today, but I do want to try to give us a chance to take a look at this in class today if you have a device once it's past 10. So in any case, these Canvas quizzes are a small portion of your grade. Typically there'll be little questions about things that we did in lecture either the previous day, or easy questions about things that we just talked about to make sure you're catching on or paying attention, or it depends on the day, kind of what sorts of things will be on them. But just kind of quick quizzes. It's not a large part of your grade, but you need to have a device of some sort, laptop, cell phone, in class. Ideally a laptop, it's a lot easier to see there, but in an emergency, if you don't have a laptop, or if yours is dead for the day or whatever, cell phone will work to access the quizzes, and that's okay for those purposes. So I'm going to add some more things onto this after. It'll put like a dotted line, and so then other things it'll be to do between class today finish up that Canvas quiz will be one of those if you didn't do it already. And stuff to do over the weekend before your next lecture, including you also have, all of you have recitation tomorrow at some point in time. In recitation tomorrow, you're going to work a lot with the details of GC, Graphing Calculator program, that we're going to talk a little bit about today, but you'll talk about some of the more detailed aspects of that tomorrow as a part of some assignments you're working on for recitation. So we're going to be using it throughout the semester to help visualize what it is that we're trying to create, as well as to do computations. So, let's see. There's a lot of music going on someplace else. All right, let's see. So, what do I want to do first? I want to take a look at iMathAS. So, this first homework is due, and so you can see there's different color codings on here. The gray means it's something that's already been due, so that was due yesterday. The yellow and the red mean they're upcoming soon. Actually, yeah, I think yellow is kind of reserved for counts less or something like that. But in any case, so the green is a ways off, red is due more quickly. So just be aware that those different colors don't mean they're different parts of your grade. It's just the warning system of iMathAS about doing your work. So what I want to actually take a look at is, I'm just going to use some data from one of the questions in this extra credit assignment. So this extra credit assignment that's due next week has to do with the sections 1.1 through 1.4 in your book about extremely large and small numbers, the relationship to one another, and how you can, relate them with computations. We're going to deal with some extremely large and small numbers today. Specifically, actually, before we get to this, grab your laptop if you don't already have it out and open up GC for me, because what we're going to do involves GC. This is the window I had open last time. And if you don't have GC downloaded, the download instructions are in the announcement that's in Canvas. So grab this and open up a window of GC. We're going to do some computations, but I want to give you a chance to get that open before we do anything else here. And if you're having trouble with it, let us know. So what I wanted to take a look at, if you have this open, but, by the way, if you have this open and you do start typing numbers, it says like an equal sign. It's waiting for you to do computations. So if you write in a symbol, it can't do a computation until you finish doing something else, and don't really need a calculator to do this, but now I do. So one thing I wanted to point out about this, 56 plus 7 point something, to the 15th power. Notice the answer on this, and this is the same as, I don't know if I can zoom this or not. This is the same as like what most handheld calculators do. The scientific notation, 7.783, etc., and then E plus 12 at the end. Make sure you watch for those when you're doing these. That's just times 10 to the 12th power. But just as a note, yours may or may not show as many decimal places as mine does. Try to type in exactly what I typed and see if yours shows that many things, 7.7836238.9, or if it shows less than that before the E plus 12. I'm just saying it's E plus 12, but it's times 10 to the 12th to say it like a normal human. So how many of yours shows all these decimal places? Anyone's? No. So there's a setting in here, just to let you know, that determines how many places of accuracy it shows. That's how many significant digits your answers show. So in the File menu, one of the options is Document Settings. You can change what font you see, where to show. It says Show Graph. You can see I was doing a graph before on Tuesday, and it shows below. You can have the graph to the right, below, above, things like that. But one of the things that is at the top here, precision, significant digits, mine's set at 10. I think the default is 6 or something like that. So you can change it to be whatever you want. If you're doing computations and you just need if you wanted an approximate decimal for something and you don't really want to see all of the rest of it, you can change the number of significant digits. Notice that it's not the same number as like how many decimal places of accuracy. It's just significant digits. So I've got 10 here, that means my number here has, oops, wherever it went. Oh, it's on this document. I've got 10 digits here, 7, and then 9 other numbers and a plus 12. So you can change that to be larger or smaller, but just be aware that if you had it set at something like 4, you're like, oh wow, all these numbers are coming out nice and even to just 4 decimal places. It's probably because of your document settings. So just be aware that what you see isn't, when you have these decimals, don't expect that they're all exact. It depends on what you're doing computations with, but I wouldn't expect that this would be, oh, that's exactly this, and then there's like a few more zeros at the end. I don't see any reason why this would end with any number of zeros based on the things that are being raised to the 15th power there. So in any case, just keep in mind when you see decimal numbers, it is rounding things essentially. It's showing you just a certain number of significant digits. If you had large non-decimal numbers, let's see, 7 to the 15th power. Let me do this to a different power. Yeah, so if this is just like a whole number here, 105, like, oh, well, that's going to be fine. Unless you had your significant digit set to, like 3. Maybe there's other decimals past that or something. It's not going to be decimals. We've all got whole number computations. But just watch your document settings just in case you are getting weird numbers and you're, maybe you're working with someone, they're getting different answers than you. It could be just that significant digit setting. And what you're working with, it really depends. Now, speaking of significant digits, the information that I wanted to use here was from question number 8. This question is talking about how large dollar bills are, and it asks how high a stack of dollar bills would be, how many would fit in a swimming pool, and stuff like that. So I'm not going to go through those questions, but what I wanted to use is the dimensions of a dollar bill, and all of our bills are the same size, unlike other countries, but dimensions of a dollar bill are given in centimeters here to 4 places for the first 2, and then 1, 2, 3, 4, 5, 6 for that last one. The thickness there is extremely small. So what I'd like us to work out using GC is, well, let's see, what would be the volume of a dollar bill? What would be the volume of $1 million in ones, or a million bills, however you want to think of that, in cubic centimeters and in cubic meters? So I'm going to write that out on here. So I want to show you one thing about GC that I think I mentioned last time. But you can make text blocks, and this is useful for, I don't know if any of you have done computer programming before, how you can leave like notes by your stuff so you can like explain what it is that each line in the program is doing so that someone else can understand it later. You can write in text. Oops, not with that key though. Here. New text block. It's like it depends on what version of operating system you have, exactly what keystroke you're going to need, and I have several different ones, so I always forget. These are all, there's keystrokes, but there's also just menu items. So when I had that purple block there, if I was graphing something, it would have shown up in purple. Otherwise, those colors don't really mean anything. Right now, I don't have any block in front of this. I'm in a text block. I can type things and it looks like regular font. Like, this is a text block. And if I just hit enter, I still am in the text. And what I wanted to use this for is to copy down this information so that I can not have it hidden. But a dollar bill in centimeters is 15.5956 by 6.6294 by 0.0922. All right. Now I don't need that problem anymore. So what I'd like to figure out is, what is the volume, if I can type, in cubic centimeters of $1 million bills, otherwise known as $1 million. Doesn't matter where they are, it's the same, if I spread them out or have them in a stack or whatever, it's the same volume. So if you're in a text block like this and you need to get back to a command line, you get to hit the command return or control return or option return, depending on your, one of those little buttons down to the bottom left of your keyboard, and then a return or enter. And it'll give you one of these squares, which means you're ready to do computations. So if I want to find a volume of a rectangular bill, we're just going to do length, width, and height. Now, one thing that unfortunately you can't do is copy and paste text into, at least you couldn't last time I tried, into, they update this all the time, so let me just try. Ooh, you can. You can copy and paste text now into equations, as long as it's numbers. You can't paste words into an equation. By the way, if you try to, ooh, undo. If you try to paste words in there, like if you start typing and it's accidentally not in a text block, and I try to type this, I'm like trying to type what I did before, it won't do spaces. And you'll say, oh, this isn't looking right. That means you're in a computation line. You're in a command line and it only wants to do math. So when you start typing this, at first, before I had too many letters, I don't know, it says equals -1, so I have a feeling that has to do something with the fact that there's two i's in there. And so when you have symbols next to one another, it means multiplication. So I've got I times I, which is -1, and a bunch of other things, which it doesn't know what they are, so it assumes that they're equal to 1. So when you type letters, it doesn't know that you're trying to type words. It thinks that they're variables of some sort or parameters of some sort and assigns them the value 1 for the time being until you tell it otherwise, just so you know. But if we want to find a volume, take a few minutes, see if you can find the volume in cubic centimeters of $1 million bills. And if you have this typed in, you can try the copy and paste, which apparently now works. I'm happy to know that.
If you're having trouble with GC, raise your hand and let us know, and we can help you out with it.
Yeah, whether it's getting it started or anything else. And if you don't have a laptop or something with you, it doesn't work on cell phones, but if you want to keep on with somebody else and think about how you do computations manually, have $1 bill and want to find its volume. That's just, well, it's this. Let's see. I'm going to do the copy and paste since it works. Oh, and by the way, notice if you type times, it gives you the little dot symbol. If you had something like an X that you're putting after it, the dot goes away, just like when you write math. Like you don't have to write time signs between a number and a symbol. But if you're writing another number, it'll change your, like the normal, like the asterisk sort of sign, the shift 8 or whatever, into a dot for you. So you don't have to hit anything fancy to make it look like a dot. But I want that. This would be $1 bill. So this isn't what I want as an answer, but I want to use this as kind of a starting point. So you know how, okay, this is how I find the volume of a rectangular, well, solid. It's not very solid. It's very flimsy. But this would be the volume in cubic centimeters. So I did centimeters times centimeters times centimeters of $1 bill, whatever denomination it might be. So if I want to find the volume of $1 million bills, what could I do to this? How could I alter this? Yeah, just times a million, right? If I had $1 bill and it's 1 point something cubic centimeters, if I had 1 million of them, it'd be 1 million times as large, right? 1 million times as much space it would take up. So let me ask this. What, if I were trying to find the volume of $1 million bills, why am I not taking each of the dimensions times 1 million? Like, if I did this one times 1 million, maybe I'll even I can group it in parentheses, and this one times 1 million, and the other one times, yeah. Right, yeah. Yeah, if you want to imagine it in a specific configuration, like if we stack them all up into a stack, and that was one of the questions in the homework was how tall would the stack be or something. That's one of the dimensions times however many things are in it. But if you want to think about, okay, this would be the equivalent if I'm thinking of, oh, this is the 15 times 1 million. This would be like laying them end to end to end, but still the same thickness and the same width. Like this would be having a long line of $1 bills lengthwise next to one another and calculating the volume as if it's a really, really long string of dollar bill. Or if I could imagine, I don't want, what if I put the million someplace else? If I imagined it grouped with this width, I could maybe imagine, oh, that's like putting them next to one another lengthwise, or widthwise, I guess, like putting the long sides of dollar bills and making, again, a long strip of them all flat, but laid out widthwise next to one another. Or, you know, maybe if you imagine, okay, I'm going to multiply this thickness times 1 million. And think about these being grouped together. I could imagine, okay, so I've got a height and a width, and then this thickness is what's being multiplied by 1 million. So that's like maybe making a stack that's 1 million tall. It doesn't matter what configuration you imagine. The total volume is going to be the same for any of those. Some of those are flat, rectangular shapes of various sizes, really long in one direction and not in the others, and very thin. If I think about multiplying the thickness by 1 million, then that's maybe like imagining stacking them on top of one another, but it's a stack that's 15-ish by 6-ish centimeters across and then just really tall. Well, 1 million times 0.01 tall centimeters tall, so it's not extremely tall. But this is cubic centimeters. So this goes to, I've got 3 decimal places of accuracy, but this is my 10 significant digits. If you had fewer significant digits, you might see a 0. Like if you had 6, you'd probably see some zeros in the whole number places. But in any case, we've got approximately, let's see if I can see commas here. We have about 1 million-ish cubic centimeters, 1,129,219 point something cubic centimeters. Regardless of how you want to imagine these dollar bills laid out, but just length times width times height, and then, oh, 1 million of those. however you want to imagine them arranged, put together. Now, I put in a part B while you're working on these. What if I wanted the volume not in cubic centimeters, but in cubic meters? Divide. Well, okay. So imagine our stack of dollar bills, if you want to say that. If I wanted to know the volume of that stack of dollar bills in cubic meters, I'd want to know, well, how tall that was in meters, which if I knew its height in centimeters, then how are centimeters related to meters? Yeah, 100 centimeters in a meter. Okay, so if I knew the height in centimeters, I'd divide it by 100 to get meters. What about the length and the width? Yeah, we need to divide those too, because to get this cubic centimeters, we did centimeters times centimeters times centimeters, and then times a million, because there's $1 million bills there. But the first three of these would be the volume of a single bill in cubic centimeters. If I wanted to know the volume of 1 million bills in cubic meters, there'd still be this times a million I can do at the end, just like before. You can still imagine it either way, but all of the dimensions, I want to think of those as in meters instead of centimeters. Or conversely, like, maybe this is something that you have done before, but if I've got cubic centimeters and cubic meters, the conversion between centimeters and meters is like 100 to 1. So if you're dealing with cubic versions of that, it's 100 cubed to 1. You can think of that whichever way you prefer. But, and again, every time you make a new line, it kind of changes the color on you. If you're not graphing, it doesn't matter. If you want to keep things a certain color just so it's easier to find, like color code stuff for yourself, you can use those. You can change the colors by clicking on these boxes. Like I can make this red, just say, oh, okay, this is a different part. Or this is the same question, or whatever you want to do with these. This X box here, by the way, that's to make it, if you were graphing something, doing that would make it not show up so that you could have something missing but still have the equation there and then just go back and show it later. So if you wanted to hide one equation temporarily, you could do that without having to delete the equation or delete the function that you were graphing. But when you're just typing stuff, it doesn't really matter. So in any case, if I wanted to reuse this, I can copy and paste that whole thing. Control-C, Control-V, or Command-C, Command-V. There's also menu options for that also. But each of these needs to be divided by 100. And you can just do this one by one. Notice I just put a divide and it turned it into a fraction for me. Divide by 100. Put the cursor here, divide by 100. Now each of these, instead of, I could move the decimal also, but now I've got, oh, here's the length divided by 100 to make it the length in meters instead of the length in centimeters. The width now measured in meters. The thickness now measured in meters, which is really small. And times a million gives me, it's all the same numbers, obviously you can see, but it's just over 1 cubic meter. So $1 million takes up, volume-wise, just over 1 cubic meter worth of space. Which is like, oh, okay. So, you've seen like heist movies and people trying to put millions of dollars into like a big duffel bag. It takes a lot of space. We won't even talk about the weight of all of that. But in any case, it's just over 1 cubic meter, like 1 by 1 by 1 meter. It's a little big, quite bulky. But in any case, I just wanted to point out not that calculating stuff with dollar bills is the point of this course, but just some of the features in GC. And like I said, just to play around with a little bit, some things you can do in terms of basic computations and copy and paste, and text lines versus computation lines. Yes?
Is there a way to break down the answer from a line and use it as, so instead of copy and pasting 15 times 9 all that, is there a way to bring down the 1 million number?
No, but you can certainly copy and paste this whole thing. So if I wanted to use this number and do something else with it, so the purpose is to not round it off. If you want to just literally copy, like literally copy this number, you could type it again, but you can't select and paste anything like that. But if I wanted to use this, make a new line. It'll let me. There we go. I'm going to put parentheses here, so I can say I'm going to put all the previous stuff in there, so that it's maybe easier to see and separate from other things that you might want to do with it. When you hit a parenthesis key, it automatically gives you a pair, not just one at a time. So you tend to not end up with, oh, like you have mismatched parentheses. That's really hard to do in GC because it gives you a pair at a time. Now, parentheses do behave a little bit strangely sometimes if you try to start typing in the middle of an expression that has some X's in it and you put some parentheses in. Sometimes it puts some of your items into the parentheses suddenly, unexpectedly, in which case it might be easier just to start a new line and copy and paste the things in, but luckily it's easy enough to do that. But yeah, this way there's no round-off error by using a previously computed number that only shows part of the answer, like only a certain number of significant digits. So if you just use the previous answers by actually copying the whole computation, you can do that. Now, one other thing related to previous computations. Well, maybe. It doesn't want to go away. In IMath.AS, get this back to regular side. These lines here, it says enter a mathematical expression. I could copy and paste all my computations that I just did. Now, this is not the answer to this question. I can copy and paste and enter answers like this, rather than trying to figure out where should I round this off to. If I've done the computations in GC, you can copy the whole computations there, including all the symbols, and you can see this is exactly the same thing, other than I guess I missed the first parenthesis, so it didn't copy those. But we've got this whole expression written out, and it has more places of accuracy because instead of copying the decimal answer, it copied the whole computations. On these, unless it says something like enter your answer rounded to such and such number of digits, please, you can get more accuracy in these sorts of results by just typing in the computation or copying and pasting the computation. If you're working it out in GC, you don't even have to work out the answer if you don't want to. You can just figure out what the computation would be. But if you want to look at the size of the answer, is this reasonable? Is this too small? Is this too big? Did I miss something? Take your time, work it out in GC, look at the size of the numbers, see if it looks normal, and copy and paste it here. Where it's a little bit harder to type in directly because the rectangle is so small. However, if you see this little yellow arrow here, this little yellow arrow is a place that will allow you to put in, it's a math palette, so you can type in math symbols. It's not quite as maybe easy as seeing how they all show up in GC, but you can do fractions, exponents, subscripts, roots of various sorts, things like infinity, and so forth. So, in any case, there's, I guess, Math Quill is the name of it, but it's a little math palette to help you type math stuff, so that if you're trying to type in directly, you can see there's all these lovely symbols and nothing looks pretty, but you can see a preview of what you've typed over to the right along with the result for it. So, just to let you know a few things about IMath.AS. So, let's move on to actually talking about some computations. Let's see. Let me have you do one more thing. I'm thinking about square roots. I saw this. All right, one more GC thing, and then we'll move on to constant rates of change. So here we've got a lovely geometry problem. So math warm up. Think about more than volume of a rectangle solid. I know that you can do things like adding 9s and 4s and things like that, but see if you can, using GC, find the area of the unshaded space inside the trapezoid, the stuff between the trapezoid and the circle, without doing any mental computations on your own. Just strictly using the numbers 4, 5, and 9, 2 as an exponent, pi, which you can just type the letters pi, and it turns into a pi symbol in GC. And see if you can get the result. There's reminder formulas at the bottom, but thinking about how you're going to get from this shape to the area in between. Take a few minutes and see if you can strictly follow the instructions. Don't add up anything, even though it's like, oh, I just want to do 9 plus 4. Just type 9 plus 4. And use parentheses. In one of the menus up above, there's a menu item that will help you get a square root. So I have a feeling you're going to need one. So there's probably just one messy part to this that needs a little work in advance. That's the height of this trapezoid, yeah? So just a little Pythagorean theorem. I just want to show you something that you can do when you're working on this. It'll just kind of maybe make your, why is this? I don't know why this won't quit. I don't want that there. Hold on a second. Quit. All right, let's go back to normal size graphing calculator. There we go, sorry. It was not cooperating with me. So if I wanted to express the height, I'm working out for myself, I'm just calling it h equals. When you can make kind of notes for yourself, even like this, that look kind of like formulas. What you're actually doing is defining something. We could use the symbol h later if we wanted to, but the height of this, you need a Pythagorean theorem sort of thing. You can still see the one over here, where I've got a hypotenuse of 9 plus 4 and one side that's 5. So here under the math, there is the square root, which you can see that it's just like some sort of key on your keyboard, depending on what your computer is. And then an R. I think V also works. I'm not quite sure why, but I'm just going to use that. So I need a hypotenuse of 9 plus 4. And the other side squared, 5 squared. And so just hitting that shift, like the caret sign, the shift 6, makes it an exponent that looks like an exponent. So that's kind of nice, instead of just getting the little caret key or caret symbol in there. So there's my height. Now that's an expression for it. Notice it doesn't say what it's equal to, but GC knows that's h. If I wanted to later, I could use the symbol h instead of retyping all that stuff. But what I really wanted to do is work out the formula for area of a trapezoid and then subtract the area of a circle, which involves what? So area of trapezoid, that 0.5 it said, times base 1 plus base 2. Well, base 1 was, I don't know which one you want to call it, 9 plus 9, and base 2, to follow the instructions strictly, we've got 4 plus 4. So there's that, and then I need times the height. I could actually type times h here, and it would do the computation, but that isn't really following the instructions. So I'm just going to hit times, and then copy and paste. And so that's the full area of the trapezoid, which would be 156. And I want to subtract out the area of the circle. So, yeah, I have all my parentheses in there. So area of circle pi r squared. Radius is a bit of a mess too, because it's related to the height there. But if I type pi, so type p, as soon as I type I, it's just going to turn into a pi symbol. But I'm going to type the letter I. And then I need a radius squared. So my radius is half of this. So again, I'm going to, well, I could just paste again, but I'm going to copy and paste that into here. But I want only half of that, because the radius isn't the whole height of the trapezoid, it's half the height. So if you had the cursor, like I did just after this, outside the square root sign, when I hit divide, it turns it into a fraction. And divide just the slash key. And then so over 2, now I've got my radius, and then I just need this squared. So cursor outside, and then just the shift and a 2. And then we've got our expression. And let's see, minus pi times that squared, that over 2 squared. And I don't know why I don't see a number here anymore. Oh, there it is. So there's a lot of kind of nifty features to this. The copy and paste is kind of useful. But as I was saying, you can actually use symbols. You can define things so that you don't have to type or copy and paste things over and over. If you know that you're going to need something, you can give it a symbol letter. There are certain letters that are disallowed, and that's something that you'll talk about on Friday, and we'll talk about the next time we do some of this. Like, you don't want to use the letter X, because X, as soon as you type it, it thinks you're doing something with a graph. Same with Y. Same with some other symbols. Yeah?
So if we saw something like this when doing homework, if we did like 0.5 multiplied by plus 18 plus 8.
Oh, no. So this, I just wanted to, as a demonstration, you could, yeah. Obviously, you can do whatever you want. You're allowed to add 9 plus 9 mentally. Not really a problem. But just, if you want to strictly follow the instructions, yeah, we can do this. So let's see, here. If I just did, let's see, 0.5 times, what do you say, 18, oops, I need parentheses, times 18 plus 8. And then I wanted to do times h. Since I have h defined up above as being that expression, this means the same thing. It gives me that same 156. And I could even do minus pi times h over 2, quantity squared. So it gives you the ability to define symbols so that you can reuse them later, so you don't have to retype things or copy and paste even. It's quite a nice program, and you can define lots of things in here. We're going to define functions and domains and all sorts of things, create new symbols for ourselves to be able to use. But let's get into actual math, because this class is not about finding areas of trapezoids and circles and stuff like that. But I just want to point out some of the features of this so that when you're playing around with it, you don't think that everything's hard and impossible, or everything's really weird and why don't I just use a regular calculator. There's some nice benefits that this has over like other sorts of regular calculators, and even more so than some online graphing calculators like Desmos. You can save files for this and send them to people and, you know, turn in homework. But, all right, onward. Let's talk about constant rate of change. We talked about this a little bit on Tuesday when we were talking about, because I pulled up GC and we had like y equals 2x plus 1. We talked about the fact that that 2 tells us the relationship between how x and y change. And you learned that in algebra at least, probably pre-algebra, what that means in terms of shapes. But I want to think a little bit more about what those sorts of constant rates of change are just in context without even having equations written or functions written, just what these relationships actually mean. So we'll start talking about just change, first of all. Then we'll get some symbols involved, and then we'll talk about rate of change when we've got more than one different varying quantity that we're going to compare to one another. So section 1.5 in your textbook introduced some of the same symbols we're going to be using. I'm going to go through some examples using some symbols to make sure we're on board with understanding what was meant by those certain symbols we're going to use and the differences between them. So just as an example to start with, suppose that your phone states your current programs take up 7.8 gigabytes of space. You download a new app that uses 0.5 additional gigabytes, and we want to know how much space is now used by the programs. So simple enough mathematics, and you don't need to make symbols to express this, but I want to talk about symbols that we could use for this so we can discuss the differences between them. So suppose that Z, just for lack of a particular letter that needs to be used, let Z represent the amount of space in gigabytes that's consumed by programs on your phone. So in this expression up above, there's this 7.8 gigabytes of space your current programs take up. That's a value of Z. You download a new app that uses 0.5 gigabytes. That's not exactly a value of Z. It's telling you how much, by adding this in, Z is going to change by. So we have a different symbol to represent just that 0.5 gigabytes on its own. And that's going to be this DZ here. So the D in front is used to represent a change or a variation in an amount of something that we were measuring with the other letter. So Z here is the amount of space consumed by programs on your phone. So DZ is a relative of Z. It's talking about a change in that amount, so that we can have a symbol to talk about just the change as opposed to having to have a whole different letter. Because 0.5 isn't how much is on your phone, 0.5 is how much it changed by. It's a difference, in fact, between how much we started with and how much we ended with. Now this problem expressed, we started with a certain amount of space consumed, 7.8 gigabytes, an initial value of Z. And you'll see these symbols, Z with a subscript of I, represents I for initial. An initial value, when we're changing, we're starting from somewhere and going to somewhere else. It doesn't necessarily have to happen over time, just like beginning and ending in some sense. Beginning of a situation, end of a situation, or before and after some change has occurred. So if I start with an initial value of 7.8 gigabytes of space consumed on my phone, and I end with more because I changed this by 0.5 gigabytes, we can find the value of z final, z subscript f, really easily. This is just arithmetic. But just thinking about the symbols we'd use to represent these, what is the value of z final here? Yeah, 8.3, 7.8 plus an extra 0.5, right? Put on more stuff, now it's more space. So we had an initial value of 7.8, a final value of 8.3 because we had a change of 0.5, a positive 0.5. So here, actually, let me start at my little writing thing. All right. So just what I wanted to point out about this, I don't know what color I'm on here. Oh, where did it do that? Got too many things touching one another here. All right, so let's see if this is going to work or if it's going to do weird things to me. I'm going to have to update this. So I won't write today. So in any case, we have this initial value and we had a change and we're able to find a final value. Easy enough relationship, but the key is to not get confused about what this is right here. This 0.5 gigabytes of space that's consumed is not a value of z, it's a value of a change in z. So there's no point in time when we were talking about when there's 0.5 gigabytes worth of stuff on your phone. It was just this one extra program added that. Like your phone probably started with more than 0.5 of something on it. So operating systems and otherwise. So we can assign these values. One thing that's really easy to, like, when we're talking about changes can be positive or negative. And when we're thinking about positive ones, it's easy to forget that it's, you're not thinking of it as positive. When you forget about the negatives, that's a big deal because you have to write negative signs, you don't have to write positive signs. But when you are talking about changing something, make sure you think about whether it's an increase or a decrease. Just to keep in mind what it is that's going on, whether it's once or over and over. So, I've got some issues with symbols showing up here. So, in any case, let me just kind of explain what this is meaning. So, using notation, so z initial, z final, and dz, we want to write an expression for the two things that are missing, and which are two of those three, and determine the value of the unmentioned quantity. So, let's just play along here. So I've got this description, again, gigabytes, so this time it's a computer. 14 gigs of disk space was consumed by your operating system. You've added programs that take up an additional 40 gigs of disk space. So just in terms of those same three symbols we were using before, what is this 40, for instance? Which does that pertain to? Initial, final, or change? This is the change. So this 40 gigabytes is an additional amount of disk space. So this is that change, or that DZ. When you got your computer, there were 14 gigabytes of disk space consumed by your operating system. What would this relate to in terms of initial, final, or change? Initial. So it's just the same as the previous example we did. We've got an initial amount and a change. So we can determine the final from that. What is the value of Z final here? Yeah, 54, just the sum of those two. The initial plus the change makes that final value. Now, if you had, let's see, phone filled with apps which are taking up 23 gigs of memory, you deleted 5.7 gigabytes of unnecessary ones because your phone was dying on you. Initial, final, or change, this 23 gigabytes? Initial? What about this? This is a change. Yeah, it's a negative change. So if I were to state DZ equals, I'd want to say negative 5.7 because I'm decreasing this initial value by 5.7. So if I wanted to calculate the final value, Z final, the part that I'm missing, I'd say 23 minus 5.7 or 23 plus negative 5.7. And what is that, 17.3? Yeah, adding Adding's hard. All right, so in any case, if you have a starting and an ending quantity, you can subtract them and figure out what the change is. If you have either a starting or ending quantity and amount of change, you can work just using basic arithmetic to find the missing value. But typically what we're going to be talking about is not just problems like this. We're going to talk about repeated change, or change that occurs at a specified rate, a constant rate, with respect to whatever it is, time going by, area increasing, whatever it might be. So something that changes at a constant rate with respect to something else. A lot of times it's time in our examples, but it doesn't have to be time. So we could talk about x's or z's or whatever letters you want in terms of this, but our final and initial subtracted would give us a change. But also an initial plus a change gives us our final, or a final minus the change that was done, including if it was a negative, that would be adding it back on, gives us the initial. So this dx or dz or d whatever talks about a change in that letter afterwards. So dx represents a change in x, whatever x might be representative of. dz represents a change in z, whatever z might have been. Whatever letters it is doesn't matter, but that d in front of a known previously used variable just represents a change in that variable's value, or a variation in that variable's value. So, as I was saying, we're going to talk about when one thing causes another to change, or when one thing changes, like as time changes, you've driven farther down the road. Time changes, distance-driven changes. When we've got changes that are related like that in a predictable way, or a known way, we can express a relationship between them, talking about the rate of change between them. We're going to start by talking about constant rates of change over all time. But the point of our course is to see that in reality, we can approach every sort of relationship of changes by thinking about constant rates of change, but just not over large intervals of time, or large intervals of whatever the kind of independent or basic variable is in our expression. So if I have some quantity y, maybe it's money changes dependent on time. As time goes on, you've earned more money. So if y changes because x changes, if your money changes because you've been at work longer, then we can find the change in one variable or one quantity based on how much the others changed. So if I know how two quantities are generally related, if I know that there's some sort of relationship between two things, time and money, area and claustrophobia, whatever it might be, if I have some sort of relationship, I can estimate how, at least estimate, how changing one will affect the other. So I can find dy from dx, or vice versa, if x and y are these two things that are somehow related, that I know what the relationship is. So this is called a rate of change, talking about how one's change is related to the other's change, the dy and dx, or whatever the two letters might be, the y's and x's that are changing. So the expression rate of change refers to when I have two related quantities, one of which causes the other to change, or at least the two kind of change in conjunction with one another. Whether or not I know which causes what is irrelevant, actually. But let's talk with an easy one. So driving, which I just mentioned a minute ago. Suppose you're driving, once you get on the highway, you can drive at a relatively constant speed of 70 miles an hour. Not a lot of traffic, you're just going. So this is a constant rate, this 70 miles per hour. Just investigating what that means, it seems simple enough, but every additional hours mean you drive an additional 70 miles. Most people don't have to drive in increments of full hours at a time, though. So what if you only drove half an hour? 35 miles. What if you drove for 2 hours? 140 miles, or a tenth of an hour? 7 miles? Yeah, we could figure out all of those. This is one way to say it, but since we know all of those other things, like after 2 hours, or I didn't say 5, or a half hour, or a tenth of an hour, if you say you're driving at a constant rate of 70 miles per hour, if you explain it just as, oh, every hour I go 70 miles, that's just kind of part of the story, because you know all these other things are true also. So it's just to explain it just more generally, and not just for miles per hour and hours and things like that, but for any rates of change. Just keep in mind, you don't want to explain it just in the, it's easy to think of that basic sense first, but just remember that it means a lot of other things. It doesn't just mean every hour you travel 70 miles, because you don't have to travel a whole hour. However long you travel, if you measure that amount of time in hours, how do you figure out how many miles you've traveled? Well, for any number of hours you traveled, whether it's like 0.7238 hours or 0.0006 hours, if you have a number of hours and you want to know how many miles you went, it's just times 70, just like it is for 1 or 2 or half or 1/10. Just however many hours you've traveled, as long as you have time measured in hours, that any additional time that you travel or any amount of time that you've traveled, to get the distance, you just multiply by 70. So this, every additional hour means an additional 70 miles traveled. That's the easiest way to think of it, because you say 70 miles per hour. So 70 miles, 1 hour, those go together. But so do every other pair of numbers, different by a factor of 70 for any number of hours. Multiply 70 to get by the amount of distance that takes place during that time. And notice these are not x and y, these are dx and dy. So you can imagine you're already driving. I don't know how far you've gone in the past. I don't know how far you are from home. Doesn't really matter. But if I travel an extra 3 minutes, if I can change that into hours, times 70 would give me how far I traveled during those 3 minutes, or how much my total distance traveled has changed. So you can talk about the distance traveled during that time increment, but also just how maybe you'd been driving all day. You're trying to get from here to, I don't know, Dallas or something. Who knows? Any extra distance or any extra time that you travel corresponds to extra distance. And so extra, because it's a constant rate of change that's positive, this increasing times 70 will make that increase. So this extends to things that are not driving and distances also. But just keep in mind this careful interpretation that isn't too narrow for what this rate means. So this rate of change is 70 miles per hour. So here's just what I was saying. For any additional time traveled in hours, the distance increases by 70 times as much. 70 times whatever that time is in hours gives you the number of extra miles, the change in the miles. So here's something that doesn't relate to time. Well, there's some time it takes to fill up your gas tank, but this isn't the numbers in this problem. You're filling up your gas tank, gas is $2 per gallon. So if I have this $2 per gallon, a constant rate, means every time I buy an extra gallon of gas, it costs me an extra $2. Or if I buy 4 extra gallons of gas, it costs me $8. Or if I want to be more general about this, however many gallons of gas extra that I need, any extra gas gallons that I purchase, multiply that by 2, and that's how many dollars extra that will add to my cost. Now, it's not that that is wrong to say every additional gallon means $2 more in cost. It's just very specific, and this is a more general statement that we know. $2 per gallon doesn't mean you have to buy whole gallons of gas and your cost increases by chunks of $2 at a time. It can increase by anything. Any additional gas purchase beyond, like you stop to talk to somebody, you start refilling your tank. You get 2.384 more gallons. How much does it cost? Oh, times 2. However many extra gallons of gas you purchase past, from any starting point. Doesn't matter if you're starting from an empty tank or whatever's already in your tank. The extra that you purchase beyond what's there times 2 tells you how much extra cost you have beyond what it was before we started. So in any case, it's a simple relationship seemingly, but the symbols here, notice this is the same as the symbols on the previous example, only it's a 2 instead of a 70. We're using here this X to represent gallons of gas purchased. So dx is a change in the amount of gas purchased, because you don't have to have started from 0 when you start measuring anything. You can start from any point in time during your trip to the gas station. How much extra you purchase after at any point in time times 2 gives you how much extra money you're going to have to pay. And it's extra because it doesn't go down. But y then, on its own, would have represented your total cost. dy is a change in your cost. So, for instance, if you're at one of those gas stations like the AM PM, where if you're going to use a card, it's an instant, oh, this costs 35 cents to start. Y isn't necessarily the same as 2 times X. It could be, but it doesn't have to be. You might have a 35-cent fee plus all of your gas charges. Or maybe there's some other sort of fee for something, you know, whatever other gas station problems you might have. Like you wanted a car wash, and it's also part of the number that you see on the pump. It's charging you that. So when you're looking at this expression, they'll say, oh, well, it's just Y is 2 times X. Why are we throwing all these extra letters in? Well, this is really what models the statement up there. The $2 per gallon represents every time I increase the amount of gas I've purchased, I increase my cost by 2 times that much, where the gas is measured in gallons and the cost is measured in dollars. But the total amount of gas and the total amount of dollars aren't necessarily given by the same relationship. It's not necessary that Y equals 2X. This doesn't tell us that necessarily, because our cost could be something else. Our cost could include other things aside from just the $2 per gallon. Total cost. So this, our change in cost is always relative to this when we're purchasing more gas. So again, for any additional gas purchase measured in gallons, extra cost is 2 times as much measured in dollars. And I know this seems like, oh, this is so simple. Why are we spending a lot of time on this? Because this is the basis of what we're doing all semester, which doesn't mean that the whole rest of the semester is going to be easy. It means that you need to be very careful about your wording and your symbol usage, because they mean very different things, and not everything is a proportional relationship. So we can talk about a constant rate of change. That doesn't necessarily mean that the underlying variables are multiples of one another, just the changes are. So what I mean by this is, so dy equals mdx. The change in y is a constant multiple of the change in x. That doesn't mean that y, whatever these might mean, is a multiple of x. It may be, it may not be. But the changes in one are related to changes in the other. Like that equation we had last time, I think it was y equals 2x plus 1. There's a constant rate of change involved there. Anytime I increase x by something, y increases by 2 times as much, that 2 slope. But y isn't 2 times x, it was y equals 2x plus 1. So constant rate of change doesn't indicate that y and x are multiples. Constant rate of change means that changes in y and x, or whatever your 2 variable symbols you're using are multiples of one another, specifically with a multiple, m, of 2. So you've seen the symbol m used before, y equals mx plus b. You can think of m as meaning multiple, because that's what it is. Changes in x multiplied by something make changes in y, or changes in y are multiples of changes in x. Let's see. Okay. Sorry, clock in here's broken. So let's think about this. A store sells make your own snack mix gifts. A box costs $B. Snack mix costs $2.75 per pound, which means that, well, the $2.75 per pound, that's our constant rate, meaning if I buy additional pounds of snack mix, any 1 extra pound would cost $2.75 extra, but any number of extra pounds multiplied by 2.75 would give me the extra cost that I'd incur. Or I could put some back and pay less if it's one of those sorts of stores. No, too much in my bag, I'll scoop it back into the bulk candy box and hope nobody noticed. But again, any number of additional pounds purchased, whether it's a whole number, a weird fraction, whatever it is, just a scoop's worth, whatever that is, however many pounds that is, times 2.75 tells you how much more your gift now costs than it used to. So think about what I could use for x, y, dx, and dy, and so that we're all using the same symbols. Let's say that x is the number of pounds of mix in the gift box, or in the gift, whatever you want to call this. So think about what another variable would be, what changes in those two would represent, and what m in this situation would mean. So just meanings for these. So think about what sort of thing it is and what units we'd measure this in. So X is the number of pounds of mix in this gift. Y would be something else entirely. What's the other sort of thing that's being measured in this problem aside from pounds of mix?
Total cost.
The cost, right. So there's two completely different concepts here. We've got pounds of something and dollars of something. We've got amount of mix and we've got the cost. So X and Y, two different variables, are going to be related. One's going to be related to, if X is about the number of pounds of mix, then Y is going to be about the cost. Those are the two things that are related by this rate of change we have. All right, but if X is the number of pounds of mix in the gift, what would DX be representative of? Yeah, changing the number of pounds of mix in your gift that you're putting together. So DX would be also something that's measured in pounds, but it's not representing a total number of pounds, but just the change in the weight of the gift measured in pounds. So as I do something, if I vary what I've done, like I take another scoop and add it in, change this, that amount of that scoop is maybe a value of DX. What about DY? Yeah, it's a change in cost or a variation in the cost due to increasing the amount of mix that you have in there. But the dy is just the change in the y variable. Y was the cost, so this is a change in the cost of the gift. We'd also measure it in dollars. So y and dy are going to have the same sort of units. X and dx are going to have the same sort of units. They're just talking about x is a total, like a total, in this case, number of pounds of mix. Whereas dx is just talking about a change, so that incremental, in this case, probably increase. You could take stuff out too, but changing the weight of your gift by adding or subtracting the snack mix. I'm going to say chocolate mix, but it's snacks. All right. Again, y and dy are both about money, but y is the cost of the gift, maybe, and dy is how much that cost of the gift changes. And the reason it would change is because you dx'd, because you added more or subtracted some mix to it. Yeah?
So is it reasonable to think about dx or dy as the number line, and then x and y as the plot on a number line?
So in terms of how these are all related to other, like the things we do, so if I wanted to graph x and y, I could do that. And I could also see dx and dy in the same graph. And I think there were some of those that were shown in your textbook. We'll talk about this next time. But if I think about an axis, like when we have x's and y's, I normally think of graphs. This would be first quadrant sort of stuff because I've got money and weight, which aren't going to be negative. But if I think about increasing the amount of gift, the weight in my snack mix, the cost is going to go up. If I think of that x-axis, wherever I am, any point on this graph I'm trying to construct, I could have corresponding pairs of costs and whatever. I don't necessarily know what everything is going to be because I don't know what B is, this mystery. I have to buy a box to put the snack mix in, and then the mix costs $2.75 per pound past, that. So, but every time I incrementally change the weight, it changes the cost by a multiple of 2.75. So if I increase the weight by a quarter of a pound, I'm going to do 1/4 times 2.75 increase in my weight. So just really quick, because I know class is about over, but if I were thinking, oh, well, let's see, y equals 2.75 times x. Not quite right, because that would mean that my gift box costs nothing. I'm going to make up a cost of my gift box. Maybe it's $4. So what this means is, so this is, any point here has a corresponding x and y pair that tells me for any particular, and I just made up this 4 here because I can't put a b. For any particular weight, I have a cost that goes with it. And if I incrementally change, I'm going to get a change in both of them. And often how that's done is just like maybe what you did when you're graphing lines, like pick a point, go across, and then go up. That little bit across that you want would represent a small change in the across x variable. A little incremental up, kind of like a stair-step sort of shape, would indicate a small incremental change in your vertical variable, your y in this case. So those would be your Those little stair step widths and heights would be like your dx and your dy sizes. But those don't have to be fixed. We can, change any amount, nice whole numbers, any weird decimal amounts. But in any case, we will continue with this. As I said, this is a main theme of the course, how constant rate of change helps us do everything. So we're going to investigate.